Welcome to Grade 10, Unit 6, Polygons. Lesson 1, Theorems with Triangles. The objectives for this lesson are to understand the meaning of collinear, concurrent, perpendicular, and bisector, to identify collinear points, and to know the definition of median, altitude, centroid, and orthocenter of a triangle. Collinear points. Collinear points are points that lie on one straight line, like this. These are collinear points. These ones are not, because they do not all lie on the same straight line. These ones are non-collinear points. Example, are the points A 37 and B 65 and C 15 -1 collinear? To decide, let's start by finding the equation that A and B lie on. So here are A and B. The slope of this line is y2 minus y1 over x2 minus x1, which is 5 minus 7 over 6 minus 3, which is -2 over 3. So we can create the point slope form of the line, y minus y1 equals m times x minus x1, where we can put m is -2 over 3, and x1, y1 is this point here, 3, 7. So y minus 7 equals -2/3 times x minus 3. This is the equation joining A and B together. So to decide if the 3 points are collinear, we need to work out if C lies on this line. So let's put in the point x equals 15 and see what coordinate we get. So if we put x equals 15 into this line, we get y minus 7 equals -2/3 times 15 minus 3. We're going to try and work out what the y value of this coordinate is. So y minus 7 equals -8, so y equals -1. So the coordinate is 15, -1. This is the coordinate of C, so yes, the points are collinear. Concurrent lines and angle bisectors. Concurrent lines are lines that pass through one point. An angle bisector is a line that divides an angle into two congruent angles. Here's the angle, and this is the angle bisector, because it divides this angle into two pieces which are exactly the same size. Line bisectors and perpendicular bisectors. A line bisector is a line that divides a line segment into two congruent line segments. In this example, this is the original line segment, and each of these orange lines divides the original line segment exactly into halves. These two parts of the original line segment have the same length. So all of these orange lines have to go through the midpoint of the original line segment. A perpendicular bisector is a bisector of a line segment that forms a right angle with the original line segment. So this green line here divides the blue line exactly in half and meets the blue line at right angles. The blue line and the green dotted line are perpendicular. Median and centroid. A median of a triangle is a line drawn from any vertex to the midpoint of the opposite side. So this line here starts at the vertex and meets the opposite side exactly halfway along at the midpoint. So this side and this side have exactly the same length. Every triangle has 3 medians, because we can create one median at each vertex. This is the median for this vertex. Then at this vertex, we can have this median, meeting this line halfway. And from this vertex, we can have this median, meeting this line at halfway. The 3 medians of a triangle are also concurrent. That means that they all meet at the same point. This point of concurrency is called the centroid of the triangle. Altitude and orthocenter. The altitude of a triangle is a line segment drawn from a vertex that's perpendicular to the opposite side, or to the opposite side produced. So for example, if we take this vertex here, we draw a line which meets the opposite side at 90 degrees. The three altitudes of a triangle are also concurrent, which means that they meet at the same point. This point of concurrency is called the orthocenter of the triangle. So starting from this vertex, the altitude goes across and meets this line at 90 degrees. And starting from this vertex, the altitude goes across and meets this line at 90 degrees. This point where they meet is the orthocenter. Let's see what happens when you have a right-angled triangle. The line from this vertex meets this side at 90 degrees, and in fact, because it's a right-angled triangle, the line from this vertex, the altitude, is exactly the same as the side of the triangle. Then from this vertex, again it goes across to meet this line at 90 degrees, and because of the right angle, this altitude is exactly the same as this side of the triangle. Then from this vertex, the altitude goes across to meet this side at 90 degrees. So in this case, the orthocenter, where the three altitudes meet, is this point here, which is also the vertex of this triangle. And here's a third example. This time, to draw in the altitude from this vertex, it needs to meet this side at 90 degrees. But that's not possible as it is at the moment, so we need to extend this side. Now, when we start at this vertex, we can draw in the altitude, which now meets the produced side at 90 degrees. Similarly, from this vertex, it's not possible to meet this side at 90 degrees, so we need to extend this side, and then we can draw in the altitude so that it meets the extended or produced side at 90 degrees. Then from the third vertex, it can meet the opposite side at 90 degrees, and we can extend this backwards so that all three altitudes meet at the same point. This point here is the orthocenter. We can say that PO equals 2/3 PB, QO equals 2/3 QA, and RO equals 2/3 RD, where O or O' is the centroid of the triangle. Example. Find the coordinates of the centroid of triangle JKL, where J is 710, K is 5,2, and L is 3,6. Let's draw a diagram. Here's J, here's K, and here's L, and they make a triangle. There are lots of ways to find the centroid of this triangle. Let's do it by finding the median from the vertex K, and then finding the point which is 2/3 of the way along the median. The median from K meets LJ at the midpoint, so let's start by finding the midpoint of LJ. The midpoint formula is x1 plus x2 over 2, y1 plus y2 over 2, which in this case is 7 plus 3 over 2, 10 plus 6 over 2, which is 5,8. So the midpoint is 5,8. Then the x-coordinate of M and K is 5 in both cases, so the median from K to M is going to be a vertical line. This means we can easily find the length of this line by doing this y-coordinate 8 minus this y-coordinate 2, which is 6. So the centroid, O, is going to lie 2/3 of the way along this line. 2/3 of 6 is 4. So the centroid is going to be 4 units above K. K is 5,2, so the centroid will be at 5,6. We can also draw in the other medians and check that they all meet at the same point. Theorem 6.2, Circumcenter. The perpendicular bisectors of the sides of any triangle are concurrent at a point which is equidistant from the vertices of the triangle. The perpendicular bisectors of the sides of the triangle are concurrent at a point which is equidistant from the vertices of the triangle. This point here is called the circumcenter. It's the center of a circle, which has all three vertices of the triangle on its circumference. Example: in the diagram shown, the perpendicular bisectors of triangle PRQ meet at O. If RT is 6 cm and TO is 8 cm, then find the length of RO and QO. First of all, for RO, we can use this right-angled triangle because we know that RT is 6 cm and TO is 8 cm. So we can use Pythagoras' theorem, a squared plus b squared equals c squared. And we know that 6 squared plus 8 squared equals c squared. So 100 equals c squared. So c, which is this length here, RO, is 10 cm. Then we know that these perpendicular bisectors all meet at a point which is equidistant from the three vertices. So RO, PO and QO are all the same length, so QO is also 10 cm. Theorem 6.3, Altitudes. The altitudes of a triangle are concurrent, RQ. So the altitudes of triangle ABC are the same as the perpendicular bisectors of triangle PQR. Perpendicular bisectors are concurrent by Theorem 6.2, so the altitudes of triangle ABC must also be concurrent. This point where they meet is called the orthocenter. Theorem 6.4, Angle bisectors. The angle bisectors of any triangle are concurrent at a point which is equidistant from the sides of the triangle. So the point O is the point where the three angle bisectors meet. It's called the incenter. It's the center of a circle that has the points A, B and C on its circumference. Example: in the diagram, O is the incenter of triangle PQR. If RC is 15 cm and RO is 17 cm, then find the length BO. To do this, we know that BO, CO and AO are all equal in length. We also know that RC here is 15 cm and RO here is 17 cm, so we can use Pythagoras' theorem to find OC. A squared plus b squared equals c squared, so 15 squared plus CO squared equals 17 squared. So 225 plus CO squared equals 289. So CO squared is 64. So CO is 8. BO must therefore also be 8 cm. Theorem 6.5, Altitude. In a right-angled triangle ABC with altitude CD to the hypotenuse AB, CD squared equals BD times AD. Let's have a look at what this means. Here's the altitude from C. It meets the line AB at the point D. The theorem says that CD squared is equal to BD times AD. Another way of saying this is that the measure of the altitude from the vertex of the right angle to the hypotenuse is equal to the product of the two segments of the hypotenuse. If the length of the altitude is h and the length of the two segments is a and b, then h squared equals a times b. Example: find x in this diagram. We can use the theorem h squared equals ab to find the length rs, and then we can use Pythagoras' theorem to find the length x. So, first of all, p to s is equal to pq minus sq, which is 9 minus 4, which is 5 centimeters. So rs squared is equal to 5 times 4, which is 20 centimeters. So rs is the square root of 20. And now we can use Pythagoras' theorem, a squared plus b squared equals c squared. So 4 squared plus root 20 squared equals rq squared, where rq is x. So 16 plus 20 equals rq squared. So 36 equals RQ squared. So RQ equals 6. X equals 6 centimetres. Quadrilaterals. A quadrilateral is a polygon with 4 straight sides. A diagonal is a straight line that connects 2 non-consecutive opposite vertices of a polygon. We're going to start by looking at a trapezium, which is also known as a trapezoid. A trapezium is a quadrilateral where exactly 2 of the sides are parallel. So in this case, the top is parallel to the bottom. If the 2 non-parallel sides are equal in length, it is called an isosceles trapezium. So in this case, the top and bottom are parallel, and the left and the right are the same length, so this is an isosceles trapezium. Parallelograms. A parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. So the top and the bottom are parallel, and also the left and the right are parallel. We're now going to look at 5 different proofs involving parallelograms. The first one is prove that opposite sides and angles of a parallelogram are congruent. To prove this, we're going to use the parallel lines to find alternate angles. If we draw in this diagonal from A to C, then we get a Z shape here, which creates 2 alternate angles, DCA and CAB. Also, if we use this parallel line, we get a Z shape here, and we get 2 alternate angles, DAC and ACB. Alternate angles are equal, so the green angles are equal to each other, and the purple angles are equal to each other. So the whole of angle DAB is equal to the whole of angle DCB. To show that the remaining sides and angles are congruent, we're going to use congruent triangles. Triangle ABC here is congruent to triangle CDA here, because they have the same angles and they also have this side in common. So that means that side AB is congruent to side CD, and it also means that side BC is congruent to side DA. And finally, it means that angle ABC, this one here, is congruent to angle CDA, this one here. Secondly, prove that the diagonals of a parallelogram bisect each other. Let's draw in the other diagonal from B to D. We're trying to show that these 2 diagonals cut each other in half exactly. We know that angle CDO and angle OBA are congruent because they are alternate angles, and we already have these 2 angles congruent. So, using congruent triangles, we can conclude that triangle DOC here is congruent to triangle BOA here by angle side angle, because they have this angle, this side, and this angle in common. So that means that the length DO is equal to the length BO, and the length OC is equal to the length OA. So O is the midpoint of BD and the midpoint of AC. Thirdly, prove that if the opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So we're assuming that AB and CD are equal, and AD and BC are equal. Again, we'll use congruent triangles to prove this. Triangle ACD here is congruent to triangle CAB here by side, 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 because they have this side, and also this diagonal in common. So therefore, angle ACD, which is this one here, is congruent to angle CAB, which is this one here. And also angle CAD is congruent to angle ACB. So this means that DC and AB must be parallel because the angles are alternate. And also BC and AD must be parallel. And this means that ABCD is a parallelogram. The fourth proof is that prove that if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So in this case, we're assuming that O is the midpoint of AC and also the midpoint of BD. So DO equals BO and OC equals OA. We also know that angle DOC here equals angle AOB here because they are vertically opposite. So therefore, triangle DOC here must be congruent to triangle BOA here by side, angle, side. Therefore, angle OCD equals angle OAB and angle ODC equals angle OBA. So this means that these are pairs of alternate angles. So BC and AD must be parallel lines, and DC and AB must be parallel lines. Therefore, ABCD is a parallelogram. And for the final proof, prove that if the opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So in this case, we're assuming that A and C are equal, and also that B and D are equal. We know that angle A plus angle B plus angle C plus angle D is equal to 360 degrees. So that means that 2 lots of angle A plus 2 lots of angle B equals 360 degrees, because A and C are both equal, and B and D are both equal. So angle A plus angle B must equal 180 degrees. So that means that the sides BC and AD must be parallel. Also, angle A plus angle D equals 180 degrees. That's here. So the sides DC and AB must also be parallel. So that means that ABCD is a parallelogram. Now let's have a look at a rectangle. A rectangle is a parallelogram in which one of its angles is a right angle. So first of all, we draw a parallelogram with opposite sides parallel and opposite sides congruent. And then one of these angles here is a right angle. And in fact, this means that all of the angles must be right angles. Prove that the diagonals of a rectangle are congruent. First of all, let's fill in the other right angles. If we draw in the diagonals AC and BD, we want to prove that the length AC is equal to the length BD. Again, we'll use congruent triangles to prove this. Triangle DCB, this one here, is congruent to triangle CDA, this one here, by side, angle, side, because they both have this side, a right angle, and this side in common. So that means that the length DB, the hypotenuse of this triangle, is equal to the length CA, the hypotenuse of this triangle. So therefore, the diagonals are congruent. A rhombus is a parallelogram which has 2 congruent adjacent sides. So we start by drawing a parallelogram with opposite sides parallel and opposite sides congruent. And then this time, the 2 adjacent sides are also congruent. So these 2 sides are the same length, and therefore all 4 sides must be the same length. So a rhombus has 4 sides of equal length. Prove that the diagonals of a rhombus are perpendicular to each other. Again, we'll use congruent triangles to prove this. Let's draw in the diagonals. We're trying to show that these angles here are all 90 degrees. We know that the diagonals of a parallelogram bisect each other, so the length AO is equal to the length OC. Therefore, triangle AOD, this one here, is congruent to triangle COD, this one here, by side, side, side. So angle AOD is equal to angle COD. and also angle AOD plus angle COD must equal 180 degrees because they make a straight line here. So 2 lots of angle AOD is 180 degrees, and therefore angle AOD must be 90 degrees. In the same way, all of the other angles around the centre must also be 90 degrees. Prove that the diagonals of a rhombus are angle bisectors. We know that triangle DOC, this one here, is congruent to triangle BOC, this one here, by side, side, side. Therefore, angle DCO, this one here, is congruent to angle BOC, this one here. This means that the line AC is the angle bisector of vertex C, and the same thing is true at each of the other vertices. A square. A square is a rectangle which has congruent adjacent sides, like this. Prove that if the diagonals of a quadrilateral are congruent and are perpendicular bisectors to each other, then the quadrilateral must be a square. So let's start with a quadrilateral where the diagonals are congruent and are perpendicular bisectors to each other. So that means that the lengths AO, OD, OC and OB are all equal, and all of these angles are 90 degrees. Then we know that triangle DOC and triangle COB and triangle BOA and triangle AOD are all congruent by side, angle, side. So therefore, the length DC, the length CB, the length BA, and the length AD are also all equal. Therefore, ABCD must be a rhombus, because it has 4 sides of equal length. Also, if we take this triangle here, it's isosceles, so this angle and this angle must be equal. So we can calculate the size of this angle by doing 180 minus 90 for the right angle divided by 2, which is 45 degrees. This angle, this angle, this angle, this angle, this one, and this one must also be 45 degrees in the same way. So the angle at each vertex is 90 degrees. Therefore, ABCD is a square. Let's summarise these properties of quadrilaterals. First of all, sides. A trapezium has 1 pair of parallel sides. A parallelogram has 2 pairs of parallel sides and opposite sides equal. A rectangle has 2 pairs of parallel sides and opposite sides equal. A square has 2 pairs of parallel sides and all sides equal. A rhombus has 2 pairs of parallel sides and all sides equal. A kite has 2 pairs of equal sides, but no parallel sides. Angles. In a parallelogram, opposite angles are equal. In a rectangle, all angles are right angles, 90 degrees. In a square, all angles are right angles, 90 degrees. In a rhombus, opposite angles are equal. In a kite, there is 1 opposite pair of equal angles, and in a general trapezium, there are no equal angles and no other angle properties. Diagonals. In a parallelogram, diagonals bisect. In a rectangle, the diagonals are equal. In a square, the diagonals bisect at right angles. In a rhombus, the diagonals bisect at right angles. In a kite, the diagonals cross at right angles. And in general for a trapezium, there are no properties for the diagonals. Here are the properties of sides, angles and diagonals all together on one diagram. You can pause the video if you want to have a look in more detail. Here are some different types of trapeziums. We have a general trapezium, an isosceles trapezium, and 2 right-angled trapeziums. In the general trapezium, we can't say anything about the angles, but in the two right-angled trapeziums, we can draw in two right angles, here and here. In the isosceles trapezium, we can say that it has one pair of equal sides and two pairs of equal angles. The isosceles trapezium is symmetrical down the middle. The isosceles trapezium also has diagonals of equal lengths because of the symmetry. Working with quadrilaterals. Example. If the perimeter of rhombus ABCD is 32 centimeters and the measure of angle B is 120 degrees, find the length of the diagonals. Here's the diagram. Here's the angle B 120 degrees, and we can divide this into two congruent angles of 60 degrees. If we call the side length x, then we know that 4x must be equal to the perimeter 32 centimeters, so x is 8 centimeters. And if we remove this triangle, then we can use trigonometry to find this length OB and this length OC. First of all, sine 60 is opposite over hypotenuse, which is OC over 8. So OC is 8 times sine 60, which is 6.93 centimeters. So the diagonal AC is 13.84 centimeters. Then cos 60 is OB over 8. So OB is 8 cos 60, which is 4 centimeters. So the diagonal BD is 8 centimeters. Example. ABCD is a parallelogram with AD produced to F and CB produced to E, such that the length DF is equal to the length BE. Prove that AECF is a parallelogram. So first of all, let's extend the sides. So AD is extended to F and CB is extended to E. Then we know that DF is equal to BE. So we know that AF is equal to CE. If we then join up the other sides to make a quadrilateral AECF, we're trying to prove that this quadrilateral is a parallelogram. These two angles are corresponding, so they are equal, and these two angles are alternate, so they are equal. So all three of these angles are equal. So that means that triangle ABE is congruent to triangle CDF by side, angle, side. So that means that the length AE, this length here, is equal to the length CF, this length here. So therefore, AECF has opposite sides congruent, so it must be a parallelogram. To summarise, collinear points are points that all lie on one straight line. Concurrent lines are lines that pass through one point. A bisector is a line which divides another line segment exactly in half. A median of a triangle is a line drawn from any vertex to the midpoint of the opposite side. The three medians are concurrent and meet at the centroid. Theorem 6.1. The centroid is 2/3 of the way along each median. An altitude is a line from a vertex of a triangle that is perpendicular to the opposite side. The three altitudes are concurrent and meet at the orthocenter. To summarise, a trapezium is a quadrilateral where exactly two of the sides are parallel. A parallelogram has opposite sides parallel and equal, opposite angles equal, and diagonals bisecting each other. A rectangle is a parallelogram with all angles equal to 90 degrees. A rhombus is a parallelogram with all sides congruent. A square is a rectangle with all sides congruent. This is the end of Lesson 2. Goodbye.